Let's look at this problem yet one more time. We're told that you've got these waves that are rolling past you, and that the distance crest to crest is 3 meters. And that's the wavelength. We're also told that the amplitude of these waves, the most they deviate from equilibrium, is 1/10 of a meter, 0.1 meter, or 10 centimeters. And we're told that as you stand there, the water moves up and down your leg. So the water moves 1.2 meters along your leg in 10 seconds. And we're asked to find the speed at which those waves are traveling. Now remember, any wave, whether it's longitudinal, transverse, moving or standing, it obeys this formula. We call that the wave equation, the Grand-High wave equation. And as you look at this equation, you see that you're halfway there. If I only knew the frequency, I could multiply it by the wavelength of 3 meters, and I'd be done. So that's my new goal, is to find the frequency. Well, let's see how much the water moves up and down your leg for one wave going past. Well, if we start with the crest right at your leg, it's going to go down to here when this part of the wave gets there. It's going to go down to here when this part of the wave gets there. It's going to go back up to here when that part of the wave reaches your leg. And then it's going to go back up to here when this part of the wave reaches your leg. So that means that this water is going to go 0.1 meter down and 0.1 meter down and 0.1 meter up and 0.1 meter up. So it's going to travel, it's going to move 0.4 meters in one cycle. Spelled with 2 C's. A cycle is the same thing as a wavelength, a repetition, a once up and down. Okay? Now, from this information, I can see that 3 waves pass my leg in 10 seconds. What I want is the frequency, where the frequency is the number of cycles, waves, if you will, divided by the number of seconds. Well, that's going to be 3 waves in 10 seconds, or 0.3 hertz, where hertz is cycles per second, or repetitions per second, or waves per second. So if I go in here and put in 0.3 hertz times 3 meters, that's going to give me 0.9. Let's see, there's a meter. A hertz is just another way of saying per second, and so that's going to be the speed, 0.9. Please turn to your neighbor and ask your neighbor, why did you vote that off the island? Why did you vote that off the island? Because of the holiday last week, we didn't have a tutorial last week. Our first tutorial, you're going to take, some of you today, many of you tomorrow, some of you Wednesday morning. That tutorial homework is not due this Tuesday, but following Tuesday. Everyone, regardless of when you take the tutorial, will turn in that homework next Tuesday, a week from tomorrow, at 5 o'clock. And you'll turn them in the atrium on the second floor. There's boxes underneath the large windows. One of those boxes will have your TA's name on it. The Learning Center opened, and I put a copy of the schedule up at the D2L site so you can look and see when it's staffed. Now again, the people in there are volunteers. Some of those individuals are profoundly good teachers. Some not so much. So you need to figure out which of those teachers really work for you and what times are the best for you. Okay, let's talk about the speed of sound in air as opposed to water or a metal. We know that in air, or any gas, it obeys this law that we will never use, that will never appear on the exam. What we will use is that the speed of sound in air is 343 meters per second at 20 degrees C, at room temperature. Now, if we look at this table, we can see that there's the speed of sound in air at room temperature. Here's the speed of sound in water at room temperature. And you can see that it's roughly 4 times faster. And then if we look at the speed of sound in something like steel, it's much, much faster, more than 11 times faster. And that's because the neighbors are tightly bound in this lattice work, and you can't start gossip without it getting out of hand, just racing from one neighbor to the next. Okay? Now, what we're going to do is answer this question. I'm trying to send a message to Flipper, my dolphin, and so I go out in my little boat, and I take a foghorn, I point it down towards the water, and I go, eh. Okay? Now that sound wave passes from the air into the water and travels to Flipper. And so the question is, what does Flipper experience? So that sound wave passes from air into water, where the wave speed's about 4 times faster. Which of these things change and how? The wavelength, the period, the frequency. Well, let's try to visualize this. These lines represent what we call wave fronts. Those are the compressed regions of the air. If we were to use an analogy of a water wave, it would be the crest. Okay? But in air, it's where the molecules are, the pressure is highest, the molecules are scrunched together. Now, the distance from crest to crest is a wavelength. Now, if we point this foghorn towards the water and go, eh, the wave moves towards the water. Now, right before it hits the water, we're going to set up some counters, just like at Walmart. We're going to set up 2 lawn chairs, and we're going to set up 2 counters. These counters each have one of those little devices that you push every time a customer comes into Walmart. And these counters are going to count the wave fronts that go past them. And watch what happens as the wave propagates. That first wave front hits the water and takes off. Okay? It just really is going places. It's going 4 times faster than it was in the air. And now as these waves continue to propagate, every time one gets in the water, it just takes off really fast. However, you'll notice that I'm always going to have the same reading on these 2 counters. And that's because the disturbance that causes the wave in the water is the wave in the air. we talked about the fact that when you set up a wave, the frequency of the wave is the same as the frequency of the source, the disturbance. Well, it's the wave fronts hitting the water that are creating the wave in the water. Okay? And so they have to have the same frequency. What about the wavelengths? Well, because those waves are traveling 4 times faster in the water, the distance between those wavefronts is 4 times greater in the water. But the frequency is the same. Now, if we go back to our original question, the wavelength in the water is going to get longer, the period is going to stay the same, and the frequency is going to stay the same. Now, what that means is that if I blow that foghorn towards the water and it has a frequency of 250 hertz, that's the frequency that Flipper's going to hear. Now, your gut's telling you that doesn't sound right. If you've done much swimming or scuba diving or snorkeling, you know that when your friend's yelling at you from the boat, your friend sounds different. Your friend doesn't sound the same frequency as when you're in the boat with your friend. Now, part of that has to do with the fact that, most of that has to do with the fact that high frequencies get damped out as you go deeper and deeper into the water. Now, if your friend was just singing to you with a pure tone, you would hear that pure tone at the same frequency underwater. But when you're shouting, "Shark, get out of the water, quick!" you're sending all sorts of different frequencies, high frequencies, low frequencies. Your particular voice has a special combination of frequencies that makes it you, that says, "Oh man, I know who that is." Okay? And as that special set of frequencies go down into the water, the high frequencies get damped out really quick. And all that's left is a low frequency. And all of a sudden you sound a little different, a little lower than you would if everyone was in the boat. See if your neighbor followed that argument. See if your neighbor's on the boat. Okay? Okay. Let's talk about the Doppler shift. Again, if you were standing on the side of the road when this siren came past, you could tell the exact instant that it went past you. When it was coming towards you and when it was going away from you. Okay? Right there. Okay? That's the Doppler shift. I love this cartoon. I love hearing that lonesome wail of the train whistle as the frequency of the wave changes due to the Doppler effect. That's what those cowboys are saying out there. Let's rob that train. Okay. Okay. Now, typically, the Doppler effect is explained through equations, through derivations. And this is the way I used to explain it for years and years and years. And my students would just get all frustrated and lost in the equations. And then I had an experience that changed the way I teach the Doppler effect. Shortly after I married my wife, I was at her home, and her youngest sister, who was then in high school, came home with 2 of her friends. They were taking physics. They were learning about the Doppler effect, and it was not making sense. Their teacher, like I used to, was using equations. And they asked me for help. And so I sat them down to the table, and I just started going through the equations, one after another, and deriving the formulas. And they didn't understand. Now, my sister-in-law, when she gets frustrated, she gets a little mean, and it was getting ugly, and she was getting frustrated. And so finally, in desperation, I said, ladies, let's go to the bathroom. So we got up, and we went down, the four of us, down the hall to the bathroom. I filled up the bathtub. We kneeled there at the bathtub, and I started tapping on the water. And that's how I explained the Doppler shift, and they had a huge aha. And that's when I decided, this is how I'm going to explain it from now on. So now if we would all stand up, we're going to the bathroom. What we're going to do instead is we're going to go with our mind out to a pond. And we're looking down on the pond. And in the middle of that pond, there's a skeeter bug. His name is Bob. And Bob likes to listen to some music. Bob likes him some music. Not really music, it's country and western. And because it's country and western, Bob likes to stomp him to some music. He stomp, stomp, and stomp with the music. And as he stomps, he sends ripples out into the pond. And those ripples propagate away from Bob at the speed of sound, the speed at which pulses travel on the surface of that pond. Now, this is the first pulse that he made. What you should be imagining here is a flat surface of the pond, but everywhere there's a circle, the water's just a little bit higher than the rest of the pond. These are ripples. And the ripples go out in all directions. There's the first stomp, there's the last stomp, and he's ready to stomp again. Now, if I were to put a leaf right here, that leaf would bounce up and down as these ripples went past it. And if Bob was stomping at 400 hertz, well, that's a little high. Okay, let's drop that down and say, let's say he's stomping at 20 hertz. Okay, 20 times a second. That leaf is going to bounce up and down at 20 times a second. Whether I put the leaf here, or here, or here, or up there, that leaf's going to bounce at the same frequency that Bob is stomping. Because he creates a disturbance, it moves out, and he creates another disturbance, and it moves out. Since all the pulses are moving the same speed, they reach with the same timing. Now, it turns out that Bob doesn't like to just sit still. He's restless. And so what Bob does, while he's listening to his music, but not really music, is he stomps and he slides, and he stomps and he slides, he stomps and he slides, okay? It looks graceful when you're not so big. Okay, so he stomps and he slides, and he stomps and he slides, and he stomps and he slides, and he stomps and he slides, stomps and he slides. Now folks, this circle here, the outer one, is the first ripple that he made when he was right here. That's where he stomped. Now you can see that that location is in the center of that biggest circle. He then slid to here and stomped. And you can see that this location is the center of that second biggest circle. He then slid to there and created this circle. He then slid to there and created this circle. He then slid to there and created this circle. And by the time this ripple got to there, Bob had moved from there over to there. Now you can see what's happening. Bob is bunching up those ridges, those crests, in the direction that he's moving. Because he's moving into the wave, this distance between crests is getting shorter. Now once a ripple is created on the water, it moves out at that sound speed regardless of what Bob is doing. And so if I look at that grand high wave equation, this is the speed of waves, of ripples. That has to equal the frequency times the wavelength. Now, as Bob's moving here, he's compressing the wave fronts, the crests here, and he's spreading them out over here. That means if I were to put a leaf right here, it wouldn't bounce up and down at the same frequency that Bob was stomping. If I look here, if this is the frequency of Bob, if I looked over here where Bob is coming towards me, the speed of the waves would stay the same. Okay? But now, because those crests are bunched together, the wavelength, the distance between the crests, gets smaller. And that means the frequency has to get bigger. Bigger than the frequency at which Bob is stomping. And we say that the frequency that that leaf is going up and down is Doppler shifted up. If I put that leaf back here, it's going to bob up and down slower than Bob is stomping. I can see that again from this equation. The speed at which the waves are moving stays the same, but now those waves are spread out, those crests are spread out, meaning a larger wavelength, which means a smaller frequency. Now, we don't really care about skeeter bugs on the pond. What we care about is sound. And if this is some siren that is moving towards you, if the siren has a rest frequency, the frequency you would hear if you were standing with it, if it has a rest frequency of 400 hertz, and it's coming towards you, what you hear is something higher than 400, because these crests are bunched together. And that means they're going to hit your eardrum at a quicker rate than the 400 hertz. If that source is going away from you, now these crests are spread out. They're not going to hit your eardrum as often. The frequency that you hear is shifted down. Talk to your neighbor. See if your neighbor understands qualitatively this Doppler shift. Okay. I am going to demonstrate this Doppler shift for you. Listen very carefully for the shift as it goes past you. Ready? I'm sorry. My point is, in order to hear this shift, the source has to be moving at a speed that's an appreciable fraction of the speed of sound. And trying to get this old fat boy going an appreciable fraction of that speed ain't going to happen. However, I can help you experience this with this source. What you're hearing now is the rest frequency, the source frequency. Okay? Memorize that. Okay? As it's coming towards you, you hear something higher. As it's coming away from you, you hear something lower. I bless you. Don't tell my uncle, Pope Francis, that I did that. No, we're not related. He's Catholic. Okay. Did everyone get a chance to hear the Doppler shift? Good. Okay. Okay. I sure like it, though. He's a good Pope. Okay. I show you this drawing just because it's the reason I'm not rich. This was drawn by Paul Hewitt. Paul Hewitt is the author of the #1 textbook for the conceptual physics class. I'm the author for the #2 textbook for that class. That's the way I explained it to my father. In truth, market share, he makes millions of dollars each year. He's got homes all over the world. I have 2% of the market share. I make $6.50 an hour. But anyway, this is an explanation of the Doppler Shift. Okay. So let's summarize. If you have a stationary source like that siren we just used, it produces waves, and if we measure their speed, wavelength, and period, the speed's going to be 343 meters per second if this is room temperature. And we measure the frequency, say it's 400 hertz. We measure the wavelength. And then we take that source and we move it towards you. Or we move you towards it. Same. Okay? So the question is, what changes as that source is moving towards you? What about the speed of the wave?
Same.
The same. Okay? The speed of the wave is only determined by the temperature of the air in this room. Okay? Now the wavelength, because those compressed regions are bunched together, the wavelength will be shorter. What does that do to the period of the wave? Remember those trains that were coming down the track at the same speed, but one had shorter boxcars. The period would be shorter. The time it takes for one to go past your ear would be shorter. But that means the frequency, which is one over the period, would be higher, and it would be shifted up. On the other hand, if this same source is moving away from you, that's the only difference in this slide, the speed of the wave would still be 343 meters per second, but now the wavelengths are spread out, so they're longer, making the period longer, and 1 over the period is the frequency, so it is lower. Okay? I like this cartoon. There goes one heck of a science teacher. The Doppler Effect. That's how you could get me to demonstrate the Doppler Effect. That's the only way you could get me going fast enough. And it wouldn't be enough to throw me off this building. You'd have to use Leon Johnson to get me going fast enough. Not that some of you wouldn't like to try. In the name of science, of course. Okay. What would this sound like? Now, I just told you that we can't run fast enough to hear this shift. But suppose instead of running, we were like my dog. Whenever we're in the car, they like the windows rolled down and they hang their head out there. Let's say you're in a car going 30 miles an hour towards a source, a whistle or a siren. And you get closer and closer, always going 30 miles an hour. So tell your neighbor, what is this going to sound like as you get closer and closer to the whistle, to the source? Talk to your neighbor. What's it going to sound like?
Frequency. It's going to sound like the stationary or closer to the stationary sound.
Well, that was just okay. The point of this exercise is that there are two things that often get confused. The loudness and the pitch. Now, the loudness is related to the amplitude of the wave. Okay? And that's going to get bigger the closer you are to the source. It's going to sound louder, meaning that the compressed regions are going to make a bigger assault on your eardrums, pushing them further in and pulling them further out. The frequency, the pitch, is how often those compressions push your eardrum in per second. Now, if I had a source, a whistle, that had a frequency right here, We call that the rest frequency. Because you're going towards the whistle, it would be the same if the whistle were going towards you. Because you're going towards the whistle, there's going to be a Doppler shift up. But that shift depends on how fast you're going relative to the source. And if you have cruise control set at 30 miles an hour, you're going to have the same shift all the time. It's going to sound louder and louder, but it's not going to sound higher and higher. It will sound higher than the whistle normally sounds, but it won't get higher and higher as you get closer and closer. Now here's an old exam question. You have a child on a tire swing. We're just going to look at the motion as the child goes from A to E. We won't look about coming back. And there's a whistle creating a constant frequency. Now the child hears different frequencies at different locations. At what location would the child hear the highest frequency? Would it be at B, moving towards C, or at C moving towards D, or at D moving towards E, or at E? So with your clicker, okay, last call. Oh, we're all okay. Now, this shift above the rest frequency depends on how fast the child is moving towards the source. The shift will be greatest when the child is moving fastest. Now you remember, the child speeds up as she comes down because of gravity, and she slows down as she goes up. So she's going the very fastest right here at C. So the correct answer to this would be at C, moving towards D. Okay, if you did something different, slap yourself right now. Okay? At that point, she's about to start slowing down. Think of speeding up all the way before noon, going faster and faster and faster, and right at noon, you're taking your foot off and hitting the brake, and you're slowing down all afternoon. When are you going the very fastest? High noon. Right when you're making that transition. Okay? Now, here's the key idea. Louder is different than higher. Okay? If we had a piano on wheels, and we were pounding the middle C key, and that piano was rolled towards you very quickly, what you would hear is something higher than middle C, like D. But as it got closer and closer and closer, you'd keep hearing the same note, D, 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 D. It'd just get louder and louder, okay? Which is different than higher and higher. Now folks, we have 9 minutes. In those 9 minutes, I'm going to help you with the tutorial this week. Okay? Now, some of this might seem like, oh, you know, I don't really need this information. Oh, yes, you do. You just don't know how badly you need this information quite yet. Some of you are very close to finding out. We're going to look in this tutorial about what happens to a pulse when you reach a boundary. And there's two different kinds of boundaries. There's the boundary with a fixed end. I'm going to fix this wave machine by clamping the last little bar. And you'll notice that when a wave comes in on the top, watch what happens when it hits the boundary. It comes in on the top and it comes back on the bottom. Okay? Goes in on the top, comes back on the bottom. Now we can think of that pulse traveling by neighbors pulling up neighbors. Imagine a big line of football players up here holding hands in unity before the game. We're going to win. And we send a pulse by having one of the football players jump up and pull up the neighbor. And they just kind of do this. And then we get to Fred at the end of the line. And Fred is holding on to the building. And when Fred tries to pull the building up, it doesn't go up. Fred's big, but not that big. And so Fred, by trying to pull up the building, pulls himself down. And then he sends a pulse back, neighbor to neighbor, on the bottom. Now in the process of hitting that boundary and bouncing back, the pulse crumples. And the shape of the pulse becomes very, very complex. We could determine that shape with some very powerful mathematics, a differential equation, or, oh yeah, let's not do that. Or we can play a game of make-believe. Here's how we do it. As the pulse comes in on the top, this point never moves, and a pulse comes back, reflects on the bottom. We can get that same result by pretending that there's not a wall there. There's no cockroaches behind the wall. And that the string keeps going behind the wall. Next, we pretend that there's a second pulse. There's one pulse going to the right, but there's another pulse going to the left. And this other pulse, this mental pulse, has a very special configuration. It is reflected and inverted. It's reflected across the boundary and inverted below the string. So it looks like this. And it's the same distance from the boundary. Now, why do I want that pulse? Because this point can't move because it used to be tied to the wall. Well, now I got rid of the wall, but this point is still not going to move. Why? Because when that point on this pulse reaches this wall, so does this point there. And they cancel. Likewise, when this point reaches the wall, so does this one. And they cancel. That's what the symmetry is all about. I'm always guaranteed that whatever part of this wave is at the wall, there's going to be exactly the opposite from this pulse. Okay? Now, in the process, I'm going to have a wave come in on the top. I'm going to have a wave come out on the bottom as these pass through each other. And this point will never move. Just like the original situation. Now watch what happens. If I move that original pulse 2 squares to the right, and I move the other one 2 squares to the left, they're on the same string, they have to move the same speed. Now I add up what the pulse looks like. But I only care about the pulse over here where there's no cockroaches. Here I have 3/4 and -3/4. That's going to give me 0. Here I've got 1.5 and 0. That's going to give me 1.5. And sure enough, now I'm just adding 0 to whatever the incident pulse is. And the spring's going to look like that. Now let's look a little bit later in time when that has gone 4 squares to the right, and this one's gone 4 squares to the left. Now if we add them up, that's what superposition means. Add them up. I've got 2.25 here, minus 2.25 there, that gives me 0. I've got 3 there, minus 1.5, that gives me 1.5. I got 1.5 there, minus 3/4, that gives me 3/4. I got 0 and 0. So what I'm going to get is 0, 1.5, 3/4, 0. And that's what the string would look like at that time. I then go 6 squares to the right, 6 squares to the left, and now you see that most of it is the reflected pulse. Just a little bit of overlap here. And that's 1.5 and minus 1.5 gives me 0. And then it goes to the reflected pulse. And then a little bit later, they pass through each other, and now I only have the one pulse, the reflected pulse. Now folks, what we just did with very simple mathematics that we call addition and subtraction is we saw this pulse come in, it crumpled, it almost annihilated, it came out on the other side, and then it... People, you're paying me for 2 more minutes. It's going to make a world of difference in your homework on the tutorial. Okay? Now, the leading edge has to stay the leading edge. The part of the pulse that hits the boundary first is the part that's going to leave first. That's different than a ball. A ball has to all move together. And so if the blue part of the ball hits first, the red part of the ball is leading as it moves away. But a pulse actually turns around and goes the other way. Now I have here, a simulation of a pulse coming into a fixed end, and you see it goes down. Now if I come into a free end, watch what happens. Oh, whoa, let's try that. I unfix the end. I'm going to send a pulse on top. Watch what happens when it gets here. Whoosh! It's twice the size. When it gets here, there's the pulse, twice the size. You've all seen this in real life. A wave comes into a seawall. If the wave is just this high, when it hits the seawall, it splashes up twice as high. Think of it in terms of the football players. We pass the pulse down, and now we get to Fred. He's expecting a football player, and there's nothing. It's a free end. It's like when you're pulling on your shoelaces to tighten them, and they break. Whoa! You overshoot. And suddenly Fred goes, whoa! And that sends the pulse back on top. Okay? Now, 30 seconds, I need them. With a free end, we imagine that the string goes on forever, but now we send this pulse back. It's reflected, but not inverted. Okay? And when these two pass through each other, you get something that's twice the size. Twice the size. Okay, now you're ready for the tutorial. We'll see you on Wednesday.